Find the following for the provided subspace. So in this example, we're asked to find the basis and find the dimension. And we're given this beautiful set here, H. So the first thing that we need to do is find the basis for the subspace H. So just to make this a little bit easier to see, I'm going to rewrite this set H here. I'm going to line up those variables P, Q, and R. So my first row is P minus 5Q, and then we can even incorporate a plus 0R. The second row is 7P plus 0Q plus 7R. Third row is 0P minus 5Q plus 8R. And last but not least, we have minus 3P plus 0Q plus 6R. So now that that's lined up so pretty, we can separate this out by the scalars, right? We have the scalar P, we've got a scalar Q, and we've got this scalar R. So we can separate this out. This becomes the linear combination P multiplied by the column vector 1, 7, 0, negative 3, plus the scalar Q multiplied by the column vector negative 5, 0, negative 5, 0. How fun. Plus that scalar R multiplied by the column vector 0, 7, 8, 6. Just ran out of room. So there we go. We've got that lovely linear combination, and this is, of course, such that P, Q, and R are all the weights, the scalars, the coefficients, those constants. So what we want to do now is check for a linear dependence relationship amongst these three vectors. We'll say that is V sub 1, V sub 2, V sub 3. Now, because we have more than two vectors here, we can't just simply look for scalar multiples. If you can see a dependence relationship, by all means, go for it and state that. Otherwise, to check for that linear dependence relationship, it's always easiest to create an augmented matrix. And we should say check for the linear dependence relation, if any exists. And so again, to do that, we are going to row reduce the matrix whose column vectors are V sub 1, V sub 2, V sub 3. Augment that with the 0 vector. And we only have to go to echelon form, right? We want to make sure that a pivot position exists in each column. Echelon form. So here we go. We have the matrix defined by the first column, 1, 7, 0, negative 3, minus 5, 0, minus 5, 0, and then 0, 7, 8, 6. And so we can actually simplify right off the bat here. We can simplify our second row. We can do 1/7 multiplied by the second row, and we could also do negative 1/3 times the fourth row. And so this leaves us with the matrix 1, negative 5, 0, 1, 0, 1, 0, negative 5, 8, and then 1, 0, minus 2. Alrighty, so looking at the pivot, the first pivot position, we want to use that to eliminate the entries below it. So we'll do minus the first row plus the second row to attain the new second row. And then we'll also do minus the first row plus the fourth row to attain the new fourth row. And so this is equivalent to the matrix. So our first row is still 1, negative 5, 0. We then have 0 plus 5. And then 0 plus 1 is 1. Third row still remains 0, negative 5, 8. And then we have 0, positive 5, negative 2. So our first column is good. And so we move to the second pivot position. And again, keep in mind, we only need to go to echelon form. So I'm just going to eliminate the entries below that. So we'll need to do the second row plus the third row to attain the new third row. And we'll do minus the second row plus the fourth row to attain the new fourth row. And so this is equivalent to the matrix 1, -5, 0. We still have 0, 5, 1, and then we have 0, 0, 9, and then last but not least we have 0, 0, -3. And so we can take our third and final pivot here and use it to eliminate the entry below it if we did, or if we do, let's say 1/3 times the third row plus the fourth row, we get that new fourth row. And this leaves us with the equivalent matrix 1, -5, 0, 0, 5, 1, 0, 0, 9, 0, 0, 0. And so we have attained our echelon form here. And we can see that we have a pivot position in each column. So this allows us to conclude that, therefore, since the matrix has n equals 3 pivots, or a pivot in each column, which implies that the columns of the matrix are linearly independent. The columns of the matrix are linearly independent, which implies that those three vectors, v sub 1, v sub 2, v sub 3, are also linearly independent. So they will form the basis for the subspace. So we can make our conclusion for part A. The basis for our subspace H is going to be defined by these three vectors. So again, if we go back to the beginning, we had v sub 1 defined as 1, 7, 0, -3. V sub 2 was defined as 5, 0, -5, 0. And v sub 3 was defined as the vector 0, 7, 8, 6. So here is the basis for our subspace. And then we also wanted to go ahead and find the dimension. So counting the vectors in our basis here, we can see that there is 1, 2, 3 vectors. So the dimension of our subspace H is 3. And these are our beautiful final answers.